viewers, welcome to my YouTube channel. This is Science Demystifier, and in today's video I will be teaching you organic reactions and mechanisms. Please, if it's the first time you're watching me live here on this channel, please look below there. You'll see the subscribe button. Click on it to encourage us to grow. Okay? Also comment, like and share our videos. It doesn't make sense you finish watching our videos, you just look past. No, please. Do the needful, okay? And God will bless you. God will bless you. Okay, now without wasting much of your time, I decided to make this video to help our students in the tertiary institutions, those of them offering chemistry or chemistry-related course. Okay? Organic reactions and mechanisms. It's going to be a topic that will take us a long while, but I'm going to fragment it. Okay, so today I will be taking you through part of the topic, a fragment of the topic will be discussed today, and when I'm done, we'll now look at another part we're going to be discussing in our next lesson. So follow me as I demystify the process of organic reactions and mechanisms. Let's go to the board. Okay, without wasting much of our time, let's look at some of the basic things that we need to know before we go into this topic. Remember, once more, the topic is organic reactions and mechanisms. So to understand the mechanism of organic reactions, we are expected to have known some of the things I want to explain now. One of them is types of organic reagents. Types of organic reagents. Then the next one is different ways covalent bonds can be broken during organic reactions. Different ways of covalent bonds can be broken during organic reactions. Then we'll now look at resonance and inductive effects, which are the electronic reactions that trigger our reaction mechanisms. Okay, now let's look at types of organic reagents. The first one is free radical. A free radical is an atom or group of atoms that's electrically neutral. That is to say, it is neither positive nor negative, but contains an unpaired electron. It contains an unpaired electron. For example, when the covalent bond binding the methyl group and hydrogen in CH4, that's the methane molecule, is being broken evenly, the paired electron in this bond, if it is equally shared by the participating atoms or groups, then it will result to the formation of what we call free radical. So there is methyl radical and there is hydrogen atom. Okay, so a free atom with an unpaired electron can be considered a free radical, and also a group of atoms, like in this case the case of methyl group, having a free electron can also be considered a free radical. Also, chlorine molecule can disintegrate to form two chlorine atoms when this bond here is broken. So the bond will now result in the sharing of the bonded electrons evenly between the participating atoms involved in the bonding process. Okay, now let's look at another type of organic reagents. That is number 2, what we call electrophile. Electrophile. What is an electrophile? An electrophile symbolically is represented as E+. An electrophile can be an electron deficient chemical species which attacks an electron-rich center during organic or chemical reactions. Okay? So it's an electron deficient species that attacks an electron-rich center during chemical reaction. As the name implies, electrophile. term is electron lover. So it goes for an electron. An electrophile can be a positively charged ion. For example, H plus, NO2 plus, CH3 plus. So this is a positive ion, this can be an electrophile. Being positively charged implies that it is electron deficient. So it will attack an electron-rich center during chemical reactions. Okay? So now the next type of organic reaction that we are going to look at, but before then, let me give you more examples of electrophiles. Electrophiles might not actually be a positively charged ion only. It can also be a compound with an incomplete electron structure. A compound with an incomplete electron structure like boron fluoride. It can also be aluminum chloride. When you look at the electronic structure of this compound, you will see that they contain an outermost shell with an incomplete number of electrons. So that makes them electrophiles because they are electron deficient. Now let's now go to the third type of organic reagent, which is nucleophile. Nucleophile has the symbol Nu minus. As the name implies, it is an electron-rich chemical species which attacks an electron deficient center during chemical reaction. It is an electron-rich species that attacks an electron deficient center during chemical reaction. Now, a nucleophile can be a negatively charged ion. For example, when you have this type of methyl radical, having a negative charge, also hydroxyl groups, some halogens like the fluoride ion, these are nucleophiles. Having a negative charge already implies that they are electron-rich chemical species. Okay? Now, a nucleophile can also be a compound that has a lone pair of electrons. Any compound with a lone pair of electrons can function as a nucleophile. For example, ammonia. Ammonia and water molecule. If you have done coordinate covalent bonding, you should be able to know that these compounds are lone pair of electrons and so can function as a nucleophile during chemical reactions. So, for us to go into the next item we have in today's lesson, and that is covalent bond breaking during organic reactions. Let me pause for a while. I'll be back shortly. Now, the next thing we need to look at is covalent bond breaking process in organic reactions. The type of bond breaking process that will apply to a particular compound or group is determined by the type of covalent bond that is present in the molecule. Remember, we have polar covalent bonds and non-polar covalent bonds. Now, polar covalent bonds are formed between atoms of unequal electron negativities, while non-polar covalent bonds are formed between atoms of equal or almost equal electronegativities. For example, in hydrogen molecule, the atoms of hydrogen here are equal in their electronegativity. So that makes the bond between them a non-polar covalent bond. So what it means is that there is no way this molecule is going to polarize, because the two hydrogen atoms here, they have equal electronegativities. So this type of molecule will definitely be involved in a type of covalent bond breaking called the homolytic bond breaking process. The homolytic bond breaking process is the one that results in the formation of free radicals, not ions. So that when this bond breaks at this point, the two hydrogen atoms will go separate ways with single unpaired electrons, as you can see. Okay, so this makes this one a free radical and this one also a free radical. So this type of covalent bond breaking is known as the homolytic bond breaking process. Now let's look at another type of bond breaking process, which is the heterolytic bond breaking process. Now, heterolytic bond breaking process occurs in molecules with unequal electronegativities between the participating atoms. So if the covalent bond is a polar covalent bond, then it's going to the breaking of the such bond is going to be the heterolytic breaking, covalent bond breaking. Okay, the heterolytic. Let's take, for example, in this molecule hydrogen chloride. You know that hydrogen and chlorine have unequal electronegativities, with chlorine being more electronegative than hydrogen. So, assuming that this is the bond that is holding hydrogen and chlorine together, and it breaks. When the bond breaks, the electron is going to drift towards the side of chlorine, because chlorine is more electronegative than hydrogen. So, it's going to pull the bonded electrons closer to itself, thereby making that chlorine to acquire a partial negative charge, while the hydrogen, being deficient in the electron, will acquire a partial positive charge. So you can see that heterolytic bond breaking process results in the formation of ions, not free radicals. So electrophiles, nucleophiles are products of heterolytic bond breaking process, while free radicals are products of homolytic bond breaking process. So let us go to the next item that we have, and that is resonance effect and inductive effect. I'll be back shortly. The next we have on our list is resonance effect and inductive effect. Now these are electronic effects that trigger reaction mechanisms, and they're very, very important. As far as this topic is concerned, you need to understand resonance effect and inductive effect. Now, we are starting with resonance effect. Remember that we have two types of bonds in terms of hybridization. When there is an overlap of hybridized orbitals of an atom, it results to the formation of a type of bond, a very strong bond called a sigma bond. And when there's an overlap between unhybridized part of an atom, it results to the formation of a very weak bond known as the pi bond. So in molecules with double or triple bonds, you find a combination of these types of bonds, which are the sigma bond and the pi bond. Now the pi bond is a very weak bond because it is loosely bound by the nucleus. It is loosely held by the nucleus in space. And because the force that is binding the electrons in the pi bond is very weak, these electrons are free to move. They are mobile. They can move from one place to another, resulting to what we call the resonance effect. So resonance effect is caused by the movement of electrons in the pi bond. They actually move from where the electrons are more to where the electrons are deficient, resulting to what we call the resonance effect. Now let us look at the structure of benzene. Remember that benzene has two canonical structures. that do not actually represent the true molecule of benzene. And I'm going to show you how those two canonical structures look like. So this is the first canonical structure of benzene with the pi bonds at alternate positions. And then we also have another canonical structure of benzene with the pi bonds at these other alternate positions. Now, from what was observed, none of these canonical structures could comprehensively give the structure of benzene, and that is why benzene is drawn with something like a circle inside, which shows that the movement of the pi electrons, which results in what we call resonance, can change at any time. So when the electrons in this bond drifts from here to here, I hope you are seeing it from there, it will repel the electrons in this other double bond, causing them to shift from here to here. And then the presence of the electrons here will also trigger the ones here to shift from here to here, now resulting to another canonical structure, which is what we have here. Now the movement of these pi electrons across the molecule is what we call resonance effect. And that is why this structure here is called the resonance structure of benzene. This is the resonance structure of benzene, which shows the movement of the pi electrons within the molecule. Now another example I'm going to give you is resonance effect in phenoxide molecule, phenoxide. So we were going to use that one to learn more on how pi electrons bring about resonance effect. I'll be back shortly. I'm going to give another example of resonance effect using the phenoxide ion. Now, the condition for resonance effect to take place in a molecule is the presence of paired electron or a negative charge. Presence of paired electron or negative charge, then a single sigma bond, and then a double bond, which consists of a sigma bond and a pi bond. So whenever you see these three things in the same place, sitting adjacent to each other, then it triggers resonance effect. Okay, so it triggers resonance effect. So let us see how resonance occurs in phenoxide ion. Now look at the negative charge. This is one of the conditions for resonance effect to take place. So the negative charge is going to come here where we have the sigma bond, single bond, because that place is electron deficient. And it's going to cause the electron in the pi bond here to relocate, which is what we call the delocalization of pi electrons. So now the electrons in the pi bond will move from here to the carbon atom at this point. So the resultant molecule, we have this structure. The resultant molecule, we have this structure. So now, because of the movement of this negative charge to this point, there will be a double bond now here. Okay? And then because of the movement of the electrons in the pi bond to this point, the carbon here is going to acquire a negative charge. So this will be the resultant molecule after this resonance effect. Remember that this one is still here and this one is still here. Okay? So at this point, another resonance will take place here because there is a double bond at this point and there is a negative charge at this point. So first, the negative charge is going to drift from here to form a double bond at this point, causing the pi electron here to shift, and that is the localization we're talking about. So this pi electron is going to come to this place to make this carbon atom here to acquire a negative charge. So that will give us another resonant molecule with this structure. it will give us another resonant molecule with this structure. So now I have this carbon here to be negatively charged, and then the movement of this negative charge to this point now brings a double bond at this point. So this one is still intact, okay, and then this other bond is still intact. So this is another resonance structure of the phenoxide ion. So let us see what happens next. Now here we have a single bond, and we have a double bond, and then we have a single bond. So what will happen is that the negative charge here will drift from here to this point, thereby causing this pi electron to go to the next carbon atom, which is the one here, and that will give rise to another resonance structure of the phenoxide ion. Another resonance structure of the phenoxide ion. So now I'm going to have a double bond here, then here I'm going to have a negative charge. Remember that this bond is still intact, okay, and this one is still intact because I didn't use them, okay. So this will be the fourth resonance structure of the phenoxide ion. Now finally, which is the fifth one, the negative charge here is going to drift to this place, causing this electron here in the pi bond to go back to oxygen. And that will give us the last resonance structure of the phenoxide ion. So the phenoxide ion is meant to have 5 resonance structures. So it's meant to have 5 resonance structures. So you have this bond here. Here's a single bond. Then here is a double bond because of the movement of this one. And here's another double bond. So these are the 5 resonance structures of phenoxide ion. Now I'm going to make a video on how to draw resonant structures, but for the sake of this lesson and for time, we're going to stop here for resonance effect. Okay, we're going to stop here. Now time will not permit us to go into inductive effect. So inductive effect will be discussed in details in my next video. And after inductive effect, we shall now look at reaction mechanisms and then types of organic reactions. Remember that these aspects of the topic that I introduced today, they are very, very crucial. They are very, very important to understanding this topic called organic reactions and mechanisms. So thanks for listening. If you have not subscribed to this channel, please do so. It is not nice, it's not good for you to watch somebody's content and then you don't like, you don't comment, you don't subscribe either. Please subscribe to this channel to enable us grow. Thanks for listening. See you in my next video.